Hello everyone, welcome to the 21st lecture in the series. This lecture is going to cover tree data structure. It is a continuation to the previous lecture. We were talking about trees. In this lecture, we are going to have a recap of some of the terminologies associated with trees. Followed by that, we will be looking at what binary trees and what are its variants. Then we will see how trees can be represented, and we will have some examples on this data structure, and towards the end we have some questions to test our understanding of the tree data structure. So, this is some of the terminologies which we have learnt already with the previous lecture. You know by this time that tree is a collection of nodes, and every node may have 0 or more successors, and every node will have exactly one predecessor. So, earlier we learned that in among the nodes in a tree there is parent child relationship. So, every node can have a maximum of one parent, and that is what we mean as having exactly one predecessor. And for the special node called as root or the origin of the tree, it does not have any predecessor. And all the nodes in the tree are linked by means of edges, and we call them as branches too. And successors of a node are also called by the name children, and predecessors we call them as parent. And nodes that are all children of the same parent, we call them as siblings. And at times we can even have nodes in a tree with no children, and probably those nodes will be called as leaf nodes, and they will be towards the bottom of the tree. So, here we have an example. We have exactly 4 nodes in this tree. Of course, in this tree the root is the node containing a value of dog, and you could see that the root contains exactly 2 children, one being cat and other being wolf. And cat and wolf are all, we can call them as siblings just because they both have the same parent. And the cat node has one more child, which is canine. And for when you look at the right subtree, you could see that there is only one node with the label wolf, and that node does not have any children, and so we say that wolf and canine are leaf nodes of this particular tree. Just because this tree has a set of words, we can also call this tree as a tree of words. So, here in this slide you have some other terminologies associated with trees, and you have certain definitions like length of the path will always be equivalent to number of edges that make up that path, and depth of a node, specific node say n, will be the length of the path from root to n. I hope you remember by this time that whenever we are asked to find the depth should be calculated from the root, and height should be calculated from the leaf node. So, here depth of the node is always the length of the path from the root node to that particular node n, and height of a node n is equivalent to the length of the longest path from n to the particular leaf node. So, we always estimate height from a particular leaf node, and depth and height of the tree will always be equivalent to the height of the root. So, we have here an example. The tree has 3 levels, level 0 being root node with value A, level 1 with 3 nodes B, C and D, and level 2 with nodes E and F. So, when we are asked to find the depth of the tree, you know depth has to be calculated from the root node, right. So, A is at level 0. So, A to B is one level and B to the next level is 1. So, we say that the depth of the tree is 2 in this case. And when we take into account the height, you know height has to always to be estimated from the leaf node. Here in this tree the leaf nodes are E and F. So, when we compute the height of E and F, it is going to be 0. For all other nodes, we can say that B, C and D are at a height of 1, considering either E or F to be the leaf nodes, and we say that root node A is at a height of 2. So, that is how we always estimate height and depth in a tree. Now we move on to the next type of tree, which we call it as binary tree. So the definition for binary tree is, it is a tree in which every node can have a maximum of 2 children, or it may have one child. It can be on its left subtree or on its right subtree, or in terms at times it may even have 0 children. So any tree that satisfies this condition of having a maximum of 2 or 1 or 0 child, we can call that particular tree as a binary tree. So if suppose a binary tree doesn't have any children, then we say that it is empty. And in the diagram you could see that we have a binary tree, and in the root node has exactly 2 children, a left child and a right child, and the left child again contains 2 children, which we call it as left and right. And you could see that the right child then has only one child, and when you take into account the right subtree, it doesn't have any children on its right subtree, right. So your binary tree could take any of the form, but always every node should satisfy the condition of having either 0, 1 or 2 children. So in short, we always say that binary tree is a tree such that every node has at most 2 child nodes. And if you want to represent a binary tree, we have to make use of, we may have to define the structure for a node, and the node structure should have pointers to left and right subtree. And you know, always the origin of the tree is marked by the root node. Also all the processing should naturally start from the root node in your tree. So whenever we do some operation, we always we provide root node as argument to the specific operation, because all operations can only start from the root node. If in case the root node is null, then it means that the tree is empty. Otherwise we may attempt to do any of the operations starting from the root node in a tree. So as you see in this diagram, we have a tree with 4 levels, level 0 to level 3, and the root node is 1, it is at level 0. And when you take into account the root node, it has 2 subtrees, T1 and T2. So the tree that starts from its left child 2, we call it as the left subtree, and the tree that originates from its right child with the node value of 3, its right subtree. So when you say a subtree as a whole, then it includes, say for instance, if I say the left subtree, it includes the set of nodes like 2, 4, 5, 8 and 9. And when you take into account the right subtree, it includes all the set of nodes that are descendant to the node with the value of 3. So here in this diagram, you could see that 6, 7 and 10, 11, 12, all these are nodes, and they are naturally descendants of the node with value 3, and so all of them make up the right subtree. Now we need to know what a full binary tree is. So let's carefully understand the meaning behind a full binary tree. A full binary tree is a binary tree where all the leaves are supposed to be on the same level, and every non-leaf should have 2 children. So these 2 conditions should be true for a full binary tree. So naturally it is a binary tree, and other than that it should hold 2 other conditions. One is that all the leaf nodes should be at the same level. The second condition is that all non-leaf children should have exactly 2 children. So here you could see different variants of full binary tree. So the first one is a root node with a root node alone. So it is a 1 node tree, or you can have a 3 node tree as you see in the second diagram. So that is also a full binary tree, just because all these 3 conditions hold. That is the condition for a binary tree, and the 2 other conditions that should be that is expected for a full binary tree. And always certain relationship holds in a binary tree. Say for instance, if parent is at location I, then we say that its left child is at the location 2i and its right child is at the location 2i plus 1. Of course, we will witness this when we learn the representation of binary trees using arrays. but you can generally know that certain relationship always exists between parent and child nodes in a binary tree. And as you see here, when you talk of labeling the nodes in a binary tree, always we start labeling the nodes in the binary tree from the root node. So, the root node has a value of 1, and you could see that all other nodes are being labeled from left to right. Right, as we move to the next subsequent levels in the tree, we always start labeling the nodes from left to right, and that is why we have labeled from 8 to 15 and 4 to 7 and so on. And full binary tree definition, you know, it is a binary tree with height h and no empty trees in levels 1 through h. That is what we said, all other intermediate levels should be completely filled and they should have the maximum of 2 children, right. And all nodes either have 2 children or they themselves will be leaves. So, here you could see that all the leaf nodes are at the same level. So, those two conditions hold, and so we say this as a full binary tree. So, in a full binary tree, it will always contain 2 power h minus 1 nodes, provided the height of tree is 4. So, in this case, the height of the tree is 4, and so we say that you could check very well that the tree contains exactly 2 power h minus 1 nodes. Next is the definition for a perfect binary tree. So, a binary tree where all the leaf nodes are at the same depth and all the internal nodes have exactly 2 children. So, it is almost same as a full binary tree which we saw before. So, if both full and perfect binary tree, they are more or less one and the same. Next, we see the definition for a complete binary tree. So, here the difference is that it is a binary tree in which all other levels are completely filled except the nodes at the leaf level, and at the leaf level you could see that certain nodes are filled from left to right, and you could see that some of the nodes do not have children at that level. So, here the thing to be understood with respect to a complete binary tree is it follows the principle of a binary tree, but we attempt to add nodes in the trees level by level, and we always keep filling up the levels from left to right. So, in this case, root node is level 0, it is filled. Level 1 should contain 2 nodes, it has 2 nodes, so it is filled. And when you talk of level 2, it has it can have a maximum of 4 nodes and it has 4 nodes. So, it is completely full. And the level 3, it is supposed to have 8 nodes, but we have just 3 nodes, and so we have filled the last level from left to right. So, this is how you need to fill up a complete binary tree. So, next we need to understand the difference between complete as well as a balanced binary tree. Now, just now we learnt what complete binary tree is. It is a binary tree in all other levels except the last level should be completely filled, and in the last level we should think of filling the nodes from left to right. So, here the notion of balanced is that we just measure the height of the right and the left subtree, and the difference in the height of left and right subtree should not be greater than 1. Only then we call the tree as balanced. If suppose the height of the left subtree is 5 and the height of the right subtree is 2, then the difference in their heights is 3, right. In such a case, we can't call it a balanced binary tree. So, here in this first example, you could see the binary tree being complete. As such, the difference between the left and the right subtree is exactly 1, and so we say that it is a complete balanced binary tree. And when you consider the next example, you could see that it is not at all balanced, just because you could see the level 2 does not contain it is not completely full. So, it is not complete binary tree, and here when you talk of depth, you could see that the height of the left subtree is 4, right, 1 2 3, it is 3, and the height of right subtree is 2, and so the difference is 1, and so we can say that it is balanced. So, here that subtree is not complete but balanced. And here we have some other examples or applications of binary tree. One of the applications is with respect to the construction of an expression tree. So, any compiler will make use of an expression tree to evaluate the expression, and in an expression tree all the leaf nodes will have operands and all intermediate nodes will have operators, and if so we call that as an expression tree, and it is actually a binary tree. So, in order to evaluate this expression we should go from bottom to top. So, here the leaf nodes at the bottommost level are A and B. So, we will first do A plus B, and followed by that the result of A plus B is fed as operand to the slash operator, and this result and C make up operands for slash, and the result gets evaluated. After that we move to the left subtree where we have operands x and y, they are summed up, and finally the result of left and the right subtree are multiplied. So, this is how your expression tree gets evaluated. And another example or application of binary tree is in the generation of a Huffman tree. Of course, Huffman tree is behind one of the compression algorithms, namely Huffman coding. So, its objective is to minimize coding redundancy with respect to compression. So, here you know very well, whenever we want to compress some data, the data size should get reduced, and in order to get the data size reduced we need to eliminate some of the redundancies in the data, and Huffman is one of the coding we have to eliminate coding redundancy. And in order to construct or to proceed with coding, we start with constructing Huffman tree, and that Huffman tree is actually a binary tree. And now you need to know the definition for forest. As you know, forest is a disjoint union of trees. So, the word disjoint very well clearly tells us that, imagine that we have a tree and we are deleting the root node. If we are removing the root node, then ultimately we will have two separate trees, one being the left subtree and other being the right subtree. So, those two can then be called as a forest. So, a forest is a disjoint union of trees. So, the way to obtain this disjoint union of trees is by deleting the root and also removing the edges that connect the root node with its left and the right subtree. Now, we will see some of the representation of trees. Of course, we first go with having a linked representation of tree. So, here you could see we are first talking about representation of trees, and for a tree there is no specific condition that a node should contain a maximum of 2 or 1 or 0 child or children, right. So, here a node can have any number of children. So, for representing such a trees we are going for a linked list. So, the way we define the node structure for such a linked list is we design the node in such a way that every node has two pointers, one pointing to the first child in a level and the other pointing to its sibling. So, here in this case we have a tree with 3 levels and the root being node A, and the node root node contains 3 children. And so, in order to represent this tree we go for a linked list. And so, when you talk of root node, it should have a pointer to its first child. So, the first child is B in this case, and it does not have any sibling, root node does not have any sibling, and so it should be null. And when you come to the second level we have the node B. So, when you think of representing B, there is no child for B. So, its first child should be empty, whereas it has 2 siblings. So, it will just have a pointer to the first sibling, which is C. And similarly with respect to C, C has a sibling as well as C has children, right. So, C will have both its pointers used. So, C will have a pointer to its first child, which is E, and C will have a pointer to its sibling D, and D does not have both. And so, for the node D, both the pointers should be null. And when you come to E has only a sibling but no children, so no first child, so it should be null, and its sibling should be marked as F or pointed to F. So now we move on to representing binary trees. As you know, in a binary tree we can have a maximum of 2 children, and so here we define the node, and the node structure contains 2 pointers, one pointing to the left child and one pointing to the right child. So this is going to be the node definition: struct node with one data field named data and 2 other self-referential structures which are pointers to another nodes, and they are named as left and right. So this is going to be the node structure. So here we have the root node and its left and right pointers, and if suppose the tree is tree doesn't have any left and right subtree, then these pointers should be null. Otherwise they will be pointing to some other nodes, and that is how we arrive at this final structure. And next is array representation of trees. When you talk of array representation, it is very interesting. So here whenever we want to represent trees with the help of arrays, the first and foremost we have to define an array, and we need to have the array size or array's capacity in such a way that it is capable of holding all the elements that are part of the tree. And when we go for array representation of trees, we do not store element at a of 0. So we know very well that certain relationship holds between parent and child in a binary tree. So if parent is at location I, its left child would be at location 2i, and its right child would be at location 2i plus 1. So here just we keep track of left and right child by 2 into I and 2 into I plus 1. We avoid I having a value of 0, and that is the reason we do not put any elements at a of 0. We always start assigning elements from a of 1, and naturally the root node will be at a of 1. So here we have an example. So here as I said, the array index starts from 1, and that is where we have the root node, which is 15 in our case. And for the root node, its left child is 8 and right child is 20. If this is treated as 1, I is equal to 1. So 1 into 2 is 2, 1 into 2 plus 1 is 3. So that is why 8 and 20 are getting stored at locations 2 and 3. So here we have another example. So we look at location a of I. A of I has a value of 11. So it is parent to 18 and 12. So naturally 18 and 12 should be at location 2 into 5, which is 10, and 2 into 5 plus 1, which is 11. So that is where 18 and 12 should have got stored. So here there is a mistake, it should have been 18. So this is how binary trees are actually represented using arrays. So here in this example, what you see is we have an array, and the array size is exactly the same as the number of elements in the tree. So there is no wastage of space in this particular example. There are 7 nodes in this tree, and exactly we have defined the size of the array to be 7. So here we have one example where we can think of that we have just 3 nodes in this tree. That is, the left subtree is completely absent, and the right subtree is contains 3 nodes including root, right. So in this case, if I have to store this particular tree, and if I want that relationship should also to exist, that is parent at location I and left child at 2i and right child at 2i plus 1, then for this tree I should allocate 7 spaces, but of course only 3 of those spaces are going to get used, and remaining things are going to be remain idle or empty. So that is one of the drawbacks of using array representation. So we say that this kind of tree is a right skew tree just because there are no elements only in the right subtree, and so that tree alone has grown, whereas there are no elements on its left subtree, and so it appears shrunken, right. So we call such a kind of tree as a skewed tree, that is the tree that has grown to a longer height either on any one of the subtrees, right. and when we go for representing a skewed tree, and if you make use of array representation, then there would be huge wastage of space. So, in order to eliminate this drawback, the best thing which we could do is we can go for linked list representation of a tree. But as you know, when we use linked list representation, we make use of pointers, and so the memory usage would be more than what we have for arrays. Now, we have certain questions to test our understanding of the concepts, the terminologies, the binary trees which we have learnt so far. And already I mentioned how to mark the level in a tree. We know always the root is at level 0, and subsequent levels will be root plus 1, right. And if in case you start labeling the levels from 1, then it would be, in this case it would be 4. If you start labeling the levels from 0, then the depth of the tree is actually 0 to 3, right. And here the height of the tree, as you know, it should always be calculated from the leaf to the root, right. So, here the deepest leaf is here, when you consider Ted, it is at 3 hops from the root, right. And when you consider Joe, it is also at a height of 3 hops from the root, right. So, we can see that the height of the tree is also 3 in this case. And here we have a question, we have an example tree, we are asked to find what is the depth of the node that contains M. So, here you know M is located here, and always depth should be calculated from the root. So, here we start counting from the root. So, 1, 2 and 3. So, that is going to be the depth of the node. And when you are asked to find the height of the node, so we are supposed to find the height from the leaf, and that should be a leaf, that should be the deepest leaf, right. So, in our case the deepest leaf is probably n and 0, because they are at a distance of 4 hops from the root, right. They should be the deepest leaf, and we are asked to find the height of D. So, we are supposed to calculate the height of D from the deepest leaf. So, 1, 2 and 3. So, that is also 3 in this case. And here in this example, what is here in this question they have asked us what is the maximum height of a full binary tree with level nodes. So, you know, in a full binary tree we know what condition should hold. It should be a binary tree, and we are supposed to all the intermediate nodes should have a maximum of 2 children, and you know very well that all the leaf nodes should be at the same depth. So, in this case they have asked us the height. So, the height should be 3 in this case. And what is the height of a complete binary tree that contains n nodes? So, we are asking about a binary tree, and that too a complete binary tree, and always the height will be log n. And here in this question, which of these following graphs are trees? So, you know tree, the basic difference between tree and graph is that in a graph we can have cycle, that is we can have a closed path, whereas that is not permitted on trees. So, here if we consider that definition, then you could say that A and B are eligible to be trees, whereas in case of C there is a cycle, and so this cannot be called as a tree. And when we talk of when you think of D, you know there is no continuity, it is actually 2 disconnected trees, right. So, we can call them as just because they are disjoint trees, then we can call them as forest, but D is not a tree. So, here we have a question. We are given with a tree whose root is A. We are asked to find the descendants of B, ancestor of A and siblings of G. So, the root node is A, and whatever nodes you see in brown, they are all called as internal nodes, and the nodes which you see in green are all leaf nodes, right. So, in this case as such D also does not have any children. So, it can also be treated as a leaf node. Now, the question is, we are asked what is the descendant of B. Now, look at B. all these nodes have originated from B. So, D, E, G, H, I, J, K, all of them can be called as descendants of B. And what is the ancestor of A? So, you know, ancestor is actually parent of A. So, both ancestor and predecessor mean the same. So, you know very well, for a root node we can't have any ancestor, so it should be null. And the third question is, what is the sibling of G? You know, so the definition for sibling is the nodes which share the same parent can be called as sibling. So, when you consider this tree, G, H, I and J, all of them share the same parent, which is E. And so, for G, H, I and J are all its siblings. So, I hope by this time you are thorough with the terminologies associated with trees. So, with the next lecture we will be moving on to other operations which can be done on trees like traversals. Thank you for watching.